Good morning. Ellie, what are you drinking? Looks fabulous.
It's just Gatorade.
Did you have a long weekend? Gatorade in the morning is what people drink after they tied one on the night before.
It wasn't really a break, I will admit. I did a lot of work. It was mostly just homework. It was a break to catch up on homework. So,
Did you catch up?
Nope.
Me neither.
Yeah. I wish I did. I still have chemistry homework and a ton of checkpoints for math. And then I have an
Which
English
math class
essay.
are you in?
Math 141.
Is that pre-calc or calculus?
Pre-calc 1. Yeah, my teacher likes to assign a lot of homework. We get it every single day. We even had it over the weekend and the break. Yeah. And then we had like 5 80-question checkpoints due Wednesday. I'm almost done, thank goodness. But that's mostly what I was doing.
Is a checkpoint like a take-home test or something?
Well, so we have checkpoints, which is like short take-home tests, and then we have our actual test, and then we have a skills checklist that we have to do. But then we also have checkpoints on my math lab, which are just homework.
Sounds like a lot of work.
It is. It's okay though.
I know Alex can be frustrating, but I have tried to make the homework like as short as possible to still help you reinforce the things that need to be reinforced.
Yeah, I really like your homework. Your homework is pretty much my break from math work. It's quite sad, really.
That may be the first time anybody has ever claimed that they liked the homework.
I
okay.
don't mind it.
All right, so I'm going to give you guys a practice problem where you are going to write total and net ionic equations for precipitation reaction. And then after that, we're going to move on to writing more total and net ionic equations, but for a different class of reaction called acid-base neutralization. All right, so let's do one together here. Oh, you can't see what I'm writing. Now, in reality, there might be some other reactions that would happen with aluminum fluoride. It's nasty, but this will be close enough. So assume that the only thing that can happen is a precipitation reaction, and tell me what the product of the reactions or the products of the reaction are, and then give me the total and net ionic forms of that equation. So remember, precipitations are double replacement reactions where the positive ion from one of the compounds ends up with the negative ion from the others. So we're combining sodium ions and fluoride ions to make a compound, and aluminum ions and dichromate ions to make another compound. So what's the correct formula for sodium fluoride? We know that sodium makes a +1 ion because it's a group 1 metal. We know that fluoride makes a -1 ion because it's a group 7 nonmetal. So one of each of those should be the right amount to make that compound. And our other compound is what we get by combining aluminum ions. So aluminum makes a +3 ion because it's a group 3 metal. Dichromate has a -2 charge because that's the charge of dichromate, the polyatomic ion. You can also tell that dichromate has a -2 charge because there are 2 sodium +1s along with it. So if you forgot the charge of dichromate, or if you forget the charge of a polyatomic ion, lots of times you can figure it out again by just looking at how many positive things are with it. All right. So if dichromate is a -2 and aluminum's a +3, it looks like we're going to need 2 aluminums for every 3 dichromates in that formula. So the last thing that we have to do before we write our total and our net ionic equation is try to figure out whether either of these make a precipitate, whether either one of them is not soluble in water. So which have you guys settled on a method that you prefer between the two that I showed you? Do you like the list of rules in the textbook, or do you like the table in Alex? I actually really like them both, but in terms of just a yes or no answer, the table is probably your fastest bet. Oh, the chat is lit up. There are 4 things in the chat. I didn't see any of them until now. When the book doesn't list the solubility, is it soluble? Ezra, the normal answer is no. If there are no rules talking about it being soluble, it's probably not soluble. All right. Would it be Na2F3? Well, what would be the charge of sodium and fluorine then? So we haven't figured out how to balance this equation yet. All we've done is written the correct products. All right. We still have to balance the equation. So the way that we make the numbers of atoms work is, since there are only 1 sodiums on the right and there are 2 on the left, we need to add a coefficient there. All right. Now, I'm doing that on purpose to show you that sometimes you're going to have to go back and rearrange it a little bit, because we will here. I see 1 aluminum here and 2 here. So let's fix that. Now that also means that now we've got 6 fluorines on the left and only 2 on the right. So we can redo that coefficient. It looks like also now we have 6 sodiums over here and 2 over here. So let's redo that coefficient so we balance out our number of sodiums. Now that should balance out our number of dichromates as well. We have 3 dichromates on the left and 3 on the right now. Remember that once we get to our total and net ionic equations, polyatomic ions don't get split apart, but they stay together as an ion. All right, so what do I mean by that? Now, let's predict solubility first. If I was doing the book rules, so I know that all of you can look up Na plus and F minus in your table and see if that makes a precipitate or not. So if you look that up, it'll say that's soluble. If you look it up in the rule sheet, it will say it's soluble because all ionic compounds of group 1 metals are soluble. All right, so anything with Na plus in it, as an ionic compound is going to dissolve. So we're writing that as aqueous. There's probably no rule that talks about the solubility of this compound. Is that why you were asking, Ezra? Because you couldn't find anything about aluminum or dichromate anyplace? So if there's no rule that says anything about it, it's not soluble. All right. And I just made this example up, but on an exam, I would have looked to make sure that the compounds were either in the table or there was an easy way that you could figure out that they wouldn't dissolve. All right. So using our rule book here, yeah, there's no rules in the tables 9.2 or 9.3 that talk about either of these ions. Generally speaking, if you can't find a rule saying it's soluble anyplace, it's not soluble. All right, it'll make it precipitate. That's close enough that I wouldn't bother giving you that as like one addendum rule to the end of those lists. If nothing shows up here about either ion, the chances are it's probably not soluble. Okay. So now that we know that this is still dissolved in water and this is a solid, we know we've made a precipitate. All right, so this is a precipitation reaction. Now, I could be evil enough to give you a case where both compounds end up being soluble at the end. So if both compounds are still soluble, we haven't really done anything at all. The reason why is at the beginning, since both of these are aqueous, we have all of these ions dissolved in solution. And remember that dissolved ionic compounds split apart, they dissociate. So if both of these were aqueous, all we've done is written all of the ions in solution a different way, right? So we have to have a precipitation to actually have a reaction occurring here. We have to have a solid at the end, or else no reactions really happen. All we've done is just written all those aqueous ions collected together in a slightly different way. They're still actually dissociated in water if they're aqueous. Now, how do we write our total ionic and net ionic equations? Remember that every aqueous ionic compound splits apart into its individual ions. All right. So what ions do we have present in 3 sodium dichromates? All right. Now, each sodium dichromate has 2 Na plus ions and a dichromate with a -2 charge. So 3 of those would be a total of 6 Na plus ions in solution. And 3 dichromate ions in solution. Our aluminum fluorides, each one of those has an aluminum with a +3 charge and 3 fluorides with a -1 charge. Well, we got 2 of those, which means we have 2 aluminum +3 ions. Remember when we're writing our total and net ionic equations to write the charges of the ions in. So a total of 6 fluorides with -1 charges. I even tried to write really small. I might be able to put everything except for that solid they put on that line. So whatever. All right. What do our products look like? We have 6 sodium fluorides that are aqueous. They're still dissolved, which means that we have 6 Na plus ions in solution and 6 fluoride ions in solution. And then finally, our aluminum dichromate is a solid, so it is not dissociated anymore. It is not split apart into ions. So that is our total ionic equation. Do we see any spectator ions here? Remember, spectator ions are ions that were there at the beginning of the reaction, and they're still there at the end of the reaction. So those spectator ions, sodium ions and fluoride ions, we know that those were not an important part of the reaction. Since they were there at the beginning in solution, they're still there in the end of solution. They didn't do anything. That's why they're called spectators. They're watching from the sidelines. So if we take out the spectator ions and rewrite the reaction, we end up with the simplest form of this equation, which is just, let's look at which ions we're putting together to make the precipitate. That's all that's left over in our net ionic equation. Any questions about that? All right, I suppose that is a blessed silence. Hannah, no. So we can write total and net ionic equations for any reaction. It only really makes sense for reactions where there are things that dissociate into ions in solution, but ionic compounds aren't the only thing that dissociate into ions, okay? So we're gonna talk now about acid-base neutralization reactions, and strong acids particularly also dissociate into ions in solution. So anytime you have things that we're dissolving in water that make ions, it makes sense to write the total and net ionic forms of the equation as well. Okay, it's just a different way of writing the equation that sort of focuses on the important parts. So we see in that net ionic equation that I just went away from on the last page, at the beginning, there was a lot more stuff in this reaction than there is at the end. So our net ionic equation is our way of sort of cutting through all of the fluff and finding out the important parts of what's coming together to make our product here. And we can do the same thing. Dissociation is. Yes, that's right. As a matter of fact, Hannah, splitting apart is literally a synonym for dissociating. And Hannah, some books like to just use the term ionization instead. In other words, making ions. That's a slightly more general term because there are some times when ions form by a chemical reaction instead of just splitting apart. So that's also a decent way to think about it. All right. We'll talk more about that, and you'll really understand the difference well when we go back and talk more about acid-base equilibrium at the end of second quarter or the middle of third quarter, sometime in there. All right. So this is a topic that keeps coming back over the entire course of the year. I'll start to give you guys a little bit of a flavor for the difference between strong acids and weak acids and the way they react. But really, you'll only understand that super well when we treat it mathematically later in the year. All right. So this is the beginning of a long discussion. So first of all, if we're going to talk about acids and bases, we need to define what an acid is. That's actually kind of a hard thing to do because when we talk about acids, we could mean any one of a few different definitions. All right, so let's go over some definitions and we'll settle on the one we're going to be using for right now. But in the end, if I talk about an acid, the first thing you should be thinking about is what kind of an acid is this? Because it could be any one of a number of different ways of thinking about what an acid means. All right. So the oldest definition of what acids are comes from a scientist named Arrhenius. All right. So Arrhenius studied different things that dissolved in water. So our simplest definition for acids are things that make H plus. We can also think of that as H3O plus. So in the long run, we'll use H3O plus, but for right now, when we're writing our total and net ionic equations, it's fine for us to think about it as just H plus ions when we dissolve them in water. All right, so let me give you an example of that. So HCl is a really good Arrhenius acid because when we put it into water, it makes lots and lots of H plus ions. So what does that mean? One of our ways of thinking about that is that HCl is what we call a strong acid. In other words, it dissociates pretty much completely when we put it into water. So when we put HCl into water, it very effectively splits apart into H plus ions and Cl minus ions. Now, in reality, this is a slight oversimplification. The real deal is that when we put HCl into water, it actually reacts with water. So this is one way of thinking about what strong acids do in water, and this way will work fine for us when we're writing our total and net ionic equations. But in reality, what's happening is HCl actually reacts with water. So here's what that looks like. So HCl reacts with water by giving H plus away from itself. And when water takes an H plus, it becomes H3O plus. Really, this is just an H plus ion with a water attached to it. So this is a way of saying that H plus ions don't normally just sit by themselves in solution. They normally have a water with them. So either way of us thinking about this reaction is perfectly fine. We're going to use this way preferentially for right now because it makes it easier to balance our total and net ionic equations. All right. But it's really not that important one way or the other which way we think about this. Later on, when we start talking about acid-base equilibrium, we'll use this second way of thinking about the way HCl behaves in water, that it actually reacts with water to make H3O plus. Okay, so Arrhenius acids are anything that we put into water that make lots of H plus ions. Arrhenius bases are anything that produces hydroxide ions. So for example, sodium hydroxide, when we dissolve that in water, it dissociates to form Na plus and OH minus. So NaOH is a great Arrhenius base. Now, Arrhenius acids make a lot of H pluses when we dissolve them in water. All right, that's a very, very limited application of what we mean when we talk about an acid, because not all acids are strong enough to actually react with water to make H3O plus ions. All right, there are lots of acids out there that have H plus ions, but they're not acidic enough to give those H plus ions to water very well. So in order to have a more rounded thought process for what it means to be an acid, we've come up with a more broad idea about acids that just focuses on the fact that they have H pluses that they can give away. Not necessarily that they're going to give those H pluses away to water like an Arrhenius acid would. So that more broad definition of an acid is what we call a Bronsted acid. So a Bronsted acid is just something that can give an H plus away. Now, HCl fits that definition great. This is also a reaction that we could classify as HCl acting as a Bronsted acid because it's giving an H plus away to water in this case. A Bronsted base is something that reacts by picking up an H plus. So in this reaction, water is our Bronsted base, the thing that is accepting the H plus ion from the Bronsted acid. Now, later on in our chapter, I will give you a third definition for acids and bases that don't have anything to do with H plus at all. All right. So these first two definitions have to do in some respect with either H plus ions or hydroxide ions. So Bronsted bases don't necessarily have to have hydroxides in them anyplace. Hydroxides are very good Bronsted bases because they can pick up H pluses from a lot of things, but we don't necessarily have to have hydroxides around to think about a Bronsted base being present. So for example, if I were to react HBr and ammonia together, HBr functions as a Bronsted acid in this reaction. And NH3 functions as a Bronsted base in this reaction. So since HBr is giving an H plus away and ammonia is picking up an H plus, try and write for me the two products of this reaction. So if HBr gives away an H plus, what's left over? It has to be Br minus. So H plus and Br minus together make HBr. If NH3 picks up an extra H plus, it turns into NH4 plus. Notice there's one more hydrogen than before, and it was neutral before, so an H plus being added to it would give the whole thing a positive charge. Now, we also have come up with the idea of talking about what these products should be called, all right? So whatever we talk about as the thing that's left over after the Bronsted acid gives away a proton, we refer to that thing as the conjugate base. So the conjugate base is whatever is left over after the Bronsted acid gives away a proton. The thing that's left over after the Bronsted base picks up a proton is referred to as the conjugate acid. So we talk about this because there are some acids and bases that don't react completely. In other words, we might have, instead of a one-way arrow here, an equilibrium arrow, another arrow pointing the opposite direction. So sometimes a conjugate base can react to pick a proton back up from the conjugate acid, and that would send the reaction in the other direction. So this conjugate base can sometimes function as a base. It can function by picking up a proton someplace else. Sometimes this conjugate acid can function as an acid, can give away a proton to something else. So that's why we've come up with those names to describe the products of a Bronsted acid, Bronsted base reaction. Now, we're going to focus more or less on Arrhenius acids and Arrhenius bases for this chapter, okay? So with that said, I want to look at the difference between what we classify as a strong acid versus a weak acid and how that relates to our definition of Arrhenius acid. So strong acids, and I think I've given you this definition, are acids that dissociate completely in water. Now, this is a little bit of a white lie, all right? I'm going to be upfront about that. So when I lie to you, I'll tell you that I'm lying, and there's a good reason behind why I'm lying, all right? Now, do strong acids dissociate completely in water? No. The reality is that they dissociate so much in water that the amount of the strong acid that's left over in water is almost completely negligible. So is it really a lie to say that this reaction is a complete reaction if there are 10 to the 7th as many times HCl's as there are H3, or sorry. So if this reaction goes to completion, there will be about 1 million times as many H3O pluses left over as there will be HCl's. Is it a lie for us to say that that's a complete reaction? Yes, but only in formality sense, right? It is more or less a complete reaction at that point. So that's what I mean when I say a strong acid is an acid that reacts more or less completely with water, all right? It's a short list. You should remember a few strong acids. So strong acids that I want you to remember: HCl, HBr, HI, HNO3, H2SO4, which is a weirdo. So I'm going to put stars all over there to let you realize that it's a weirdo. It's a weirdo because H2SO4 has 2 protons, H2, right? But only one of those protons is given away easily to water. All right, so one of the protons is a strong acid proton, and the other proton is a weak acid proton. So that's another way of saying that H2SO4 is a strong acid, and HSO4 minus is a weak acid. Perchloric acid is another strong acid. We don't use this one that often, so I don't care if you really remember it. There are a bunch of other strong acids, all right? For right now, if I give you an acid that isn't on this list and it's a strong acid, I'll tell you it's a strong acid. If it's not on this list and I don't say anything about it being a strong acid, assume it's not a strong acid. Assume it's a weak acid, all right? Now, remember that weak acids do not dissociate completely in water. So what does that mean? I think I gave you a couple of examples. So one conspicuous acid that is not on the strong acid list is HF. It's conspicuous because all of the other hydrogen halides are strong acids, all right? HCl, HBr, HI, all of those split apart completely in water. HF does not. It's a weak acid. So what does that mean? We can dissolve HF in water just fine. It dissolves, but it does not split apart when it dissolves. It doesn't dissociate in water. So does that mean that it won't react with water at all? No, it just means that it only reacts with water a little bit. So if we were to write a reaction between HF and water, instead of writing a one-way arrow, we would write what we call an equilibrium arrow. All right, so what this means is that this reaction can go in either direction. So does HF make ions when we put it into water? Is it an electrolyte? Yes, but it's a really bad electrolyte. We call it a weak electrolyte. The reason why is HF only reacts with water a little bit. So if we were thinking about how many ions we're making when we put HF in to react with water, in the equilibrium, the balance between reactants and products here, there would probably be about 10,000 sets of reactants to every one product. Just a rough guess, all right? But pretty close to right. So what that means is that HF only reacts with water a little bit, not completely. That also means that when we go to write our total and net ionic equations with weak acids, we have to remember that even though they're written as aqueous, we do not dissociate weak acids in water. They don't split apart to make H plus and F minus, for example. So this background is getting us to a place where we can start to predict the products of neutralization reactions. All right. Now, there are lots of neutralization reactions. The general way that we describe a neutralization is mixing together an acid, which is some sort of a solution with a low pH, with a base solution that has a much higher pH to make a neutralized solution with an intermediate pH, a pH in between those two. So that's what neutralization is. All right. If you have ever added together, for example, sodium bicarbonate and vinegar to make your baking soda volcano, that's a neutralization reaction. It happens to be a neutralization reaction that produces lots of bubbles of carbon dioxide while you do it. But if you measured the pH of your vinegar solution and you measured the pH of the solution after you added the vinegar or the baking soda to the vinegar, the pH would be much, much higher than it was than the vinegar itself was at the beginning. Yeah, Hannah, with all the wind, I'm sure that there's going to be some problems today with power. So if we go dark, it's probably just that my power went out. It could definitely happen to me too. I can hear the wind screaming outside right now. But until it does go dark, we're going to keep on trudging ahead. We're going to do our best. Okay. So when I talk about a neutralization reaction in more specific terms, the ones that we're going to talk about right now the general form for what those kinds of neutralization reactions are going to look like is we're going to add some kind of an acid. Remember that acids, the way that we've defined them so far, generally have something to do with having H plus. So H plus and hydroxide, OH minus, when we put those together, we get water. This is also a double replacement reaction, all right? It's just a double replacement reaction where water is one of the products. So let's look at a very simple example of a neutralization. If we put HCl together with sodium hydroxide. The double replacement reaction that happens is we have H plus getting together with OH minus to make water. So water is always the product of a neutralization where we're adding an acid to a hydroxide salt. Water is always one of the products. We also have to make an ionic salt from the other two things that we're putting together. So if H plus and OH minus get together, then Na plus and Cl minus get together to make our other product. And we know that because all group 1 ionic compounds are soluble, that's going to be aqueous. We're just going to make liquid water our product here, all right? So there's no such thing as aqueous water because aqueous literally means dissolved in water. If we make water a product of the reaction, it has to be some state of matter, solid, liquid, or gas. Most of the time, if we're doing these reactions in aqueous solution, then water is at the temperature where if we make it, it's going to be a liquid. So if we want to write this equation, this neutralization, as a total ionic equation, our rules for writing total ionic equations tell us that any ionic compounds that dissociate are written as individual ions. Any compounds that dissociate are written as individual ions. So besides just soluble ionic compounds, strong acids also dissociate. They're also written as individual ions in the total ionic equation. So when we write this total ionic equation to describe this reaction, instead of HCl, we're going to write that as H plus ions in solution and Cl minus ions in solution. Sodium hydroxide is a soluble ionic compound, so we follow the rules for total ionic equations and write it as its individual ions, Na plus and hydroxide in solution. So those are our reactants in the total ionic form of this equation. Our products are water, which water is just liquid water, it's not dissociating. So water is one of our products of the reaction, but sodium chloride is still dissolved in water, so we're still going to write those ions dissociated. Oops. So there's our total ionic form of this equation. Just like with all of the other total ionic equations we've written, we can look for spectator ions to try and simplify this to make a net ionic equation. And I can see that Cl minus and Na plus were there in the beginning of the reaction, and they're still there at the end. Those are our spectator ions. So writing this reaction without the spectator ions gives us the net ionic equation. In the end, anytime we react a strong acid with a hydroxide base, this net ionic equation or some multiple of that is going to be the answer. So if we had a hydroxide containing base with more than one hydroxide, like for example calcium hydroxide, or any of the larger group 2 hydroxides are soluble. Barium hydroxide would be another example. All right, we don't see strontium hydroxide that often in undergrad labs, but I mean, it exists. Any larger group 2 metal hydroxides, if those react with a strong acid, let's just do an example of that. Holy smokes, we just finished a nothing nicer than a brand new tablet of paper. All right. So let's see another example when we put together a strong acid. So nitric acid is on our list. All right, that's a strong acid. And a hydroxide base. This time we'll use barium hydroxide instead because it's going to make the stoichiometry of the reaction a little bit more complex and interesting. So what are our products of this reaction? And then write for me the total and net ionic forms of this equation. I'm going to grab some more hot coffee. I'll be back in a second. Remember double replacement reaction. What do we get when H plus and OH minus get together? We have waters. That's always one of the products of an acid-base neutralization when we're using hydroxide bases anyway. Our other product has to be what we get when we put barium ions and nitrate ions together. So what is the charge of barium in an ionic compound? It's a +2. It's group 2 metal. What is the charge of nitrate? The nitrate ion has a charge of -1. So the correct formula for barium nitrate should have 2 nitrates for every barium. And if you look up the solubility of barium nitrate, you'll see in the solubility rules that any nitrate is soluble. So the nitrate ion makes any ionic compound soluble. So that's aqueous. Now, this is not a balanced equation. You can see that because there's only 1 nitrate on the left. There's 2 nitrates on the right. How do we balance it? Well, by putting a 2 in front of HNO3, we balance our number of nitrates. Now, that also unbalances something else. Now, one way that we can think about this is how many waters should we be making? If we're giving away 2 H pluses and we have 2 hydroxides to pick them up, then that means in the end we're going to be making 2 waters here. So if we count our atoms, that will be a balanced chemical equation. It's a little hard to think about balancing this one because of oxygen. The reason why is when we balance nitrates, there are oxygens in those, but then we have to worry about balancing the oxygens that aren't a part of nitrates also. And that's where the confusion is here. All right. So the easy way for me to balance neutralization reactions is to think about how many waters I should be making based on how many H pluses I'm giving away and how many hydroxides are picking them up. So since there are 2 hydroxides here picking them up, we know that we're going to end up making 2 waters. So now how do we write the total and net ionic forms of this equation? Well, what do we get when strong acids are put into water? They dissociate into ions. So if we have 2 of these HNO3s, that means that we're going to be making 2 H pluses in solution and 2 nitrates in solution. When barium hydroxide dissolves in water, we end up with 3 total ions, a barium 2+ ion and 2 hydroxide ions that are -1s. Oops. In the products, we have 2 waters. Water isn't dissociated, it's just liquid water is one of our products of the reaction. And we also have barium nitrate, which is still dissolved, which means it is still dissociated into its individual ions. So let's check for spectator ions. I see those 2 nitrates and our barium ion are present in the reactants. They're still present in the products. So since they're present both places, we can cancel them out. And when we rewrite our equation without, we end up with this. 2 H pluses and 2 hydroxides make 2 waters. If you wanted to say that since all of those are a multiple of 1, that we just say H plus OH minus makes water is our net ionic equation, that's perfectly fine as well. If you wanted to write it without the 2's, fine. With the 2's, also fine to me. Either one of those is perfectly fine. So the reaction is described perfectly by either equation. This way of writing the equation just tells us that we're actually making 2 waters in this reaction instead of just 1. So it gives us a little bit of extra information there. Whatever, one way or the other, fine with me. So how would the equation change if we used a weak acid in a neutralization instead of a strong acid in a neutralization? So for example, HF would react with pretty much any hydroxide base very well, but it doesn't react with water. In other words, it doesn't dissociate in water. So how does that change the way we write our total and net ionic equations? Let's take a look. All right, instead of HF, we'll use the example of acetic acid. So that's the active ingredient in vinegar. It's a weak acid. What if we mixed acetic acid with potassium hydroxide? So writing the products, still the same way, all right? We're still gonna make water and some kind of ionic salt. So what would our products look like of that reaction? Remember, acetic acid is just the acid that comes from the acetate ion. The acetate ion is buried in there. So Hannah, why would you think it would be the strongest acid? I'm trying to think where that comes from. I mean, really, acetic just plays off of the name acetate, right? So remember that whenever we turn a polyatomic ion name into an acid name, we drop the suffix ate and turn it into an ic. So acetate becomes acetic. And the other thing that I want to remind you guys of is strong acid doesn't mean dangerous, and weak acid doesn't mean not dangerous. I would rather work with HCl or HBr or HI, all three of which are strong acids. I would work with any of those three all day, every day, over working with HF, which is a weak acid. HF is really, really dangerous stuff. You can't even store it in glass containers because it dissolves glass. Yeah, it has to be stored in Teflon-lined containers because it destroys glass. As a matter of fact, commercially, it's used to etch glass. So if you ever see intricate frosted designs on glass, that was made by penning hydrofluoric acid onto the surface and letting it eat away at the surface for a while and then rinsing it off to create that frosted look. Cool, but also super dangerous. Water and an ionic salt. So water is one of our products here. The other product is what we get when we put potassium ions and acetates together. Potassium, group 1 metal, +1 charge. Acetate, the acetate polyatomic ion has a -1 charge. So we only need one of each of them to make our product. Now, the total and net ionic equations are where things are going to get different because of how we define weak acids. Weak acids don't dissociate in water. So this is our first case where we have something that's aqueous, but it's not splitting apart in water, all right? Even though it does just a little bit, we're going off of what the bulk of what acetic acid or other weak acids do, which is even though they dissolve in water, they don't split apart in water. They don't dissociate. So when we write our total ionic form of this equation, we're going to keep that weak acid together. We're not going to dissociate it. Potassium hydroxide, though, is a soluble ionic compound. So just like before, we're going to split it apart in water, just like all soluble ionic compounds. Water is one of our products of this reaction. Potassium acetate is actually double super soluble, not just plain soluble. The reason why is having potassium, a group 1 metal ion, in any ionic compound will make that compound soluble. Acetates are also all soluble without exception. So we could dissolve a metric crap load of potassium acetate into water if we wanted to do that. But in this case, all we need to know is it dissolves, which means it's still dissociated. So do we have any spectator ions here? I only see one. The potassium ions were there at the beginning and they're still there at the end. So when we write our net ionic equation, we're going to take them out of the equation, spectator ions. Now you can think about this, and it actually is sort of a fun way of thinking about the difference between the behavior of a strong acid versus a weak acid. When we look at the way this strong acid behaved in solution, it gave away its H plus right away. The H plus was just out there to be taken. So as soon as that HNO3 was dissolved in water, the H pluses were sitting by themselves. The difference is, in a weak acid, the H pluses weren't just sitting there, they were still attached to acetate. So in this case, instead of just combining with hydroxide in solution, the hydroxide had to actively steal that H plus from the weak acid. All right, it was a lot easier for the hydroxide to pick up the H pluses here because they were just sitting there in solution. They'd already been given away. In this case, that weak acid didn't want to give away its proton as much, so the hydroxide had to actively steal it away instead. Let's try another example of a neutralization reaction with a weak acid. So give me the products and then write the total and net ionic equation here. So remember, water and an ionic salt. So which ionic salt are we going to make here? We're combining lithiums and phosphates to make an ionic compound. Lithium is a +1, group 1 metal. Phosphate, the polyatomic ion, has a -3 charge. So we're going to need 3 lithiums to go with every phosphate in that product. Compounds of group 1 metals are all soluble, so lithium phosphate is aqueous. This is not a balanced equation. We got to add coefficients to do that. So if we look at how many lithiums we have on the right, 3, and how many lithiums we have on the left, 1, we're going to need a coefficient of 3 to balance our lithiums. How many waters are we making here? Well, think about the number of hydroxides and the number of H pluses that we're adding together. We're adding 3 hydroxides together with 3 H pluses to make 3 waters. So when we write our total and net ionic forms, remember that the H pluses don't actually get given away from H3PO4. In other words, it doesn't dissociate by itself in water. In other words, the hydroxides have to steal the H pluses. They're not just given away automatically. So when we write our total ionic equation, weak acids do not dissociate in water. Lithium hydroxide is a soluble ionic compound, so it does dissociate. Since we have 3 of them, we have 3 lithium plus ions in solution and 3 OH minus ions in solution. Our 3 liquid waters stay as 3 liquid waters. Lithium phosphate is a soluble ionic compound, so it is still dissociated into its 3 lithium plus ions, and it's phosphate with a -3 charge. And there's our total ionic equation. Any questions about that? So to get our net ionic equation, we have to look for and remove the spectator ions. I see those lithiums present on both sides. Those are spectators. They weren't important to the reaction. So writing the net ionic equation, we'll remove those. And there's our overall reaction. Any questions? So rest of the week schedule, on Wednesday, we are going to cover another class of reactions that mostly happen in aqueous solution, although they can happen really anywhere. So for Wednesday, if you want to be very well prepared for class ahead of time, read the section in chapter 9 that talks about redox reactions, reduction oxidation reactions, or they might call them oxidation reduction. When will we cover the next lab? When did I say we would cover the next lab? I can't remember anymore. Give me just a second to take a look. Well, shoot, we could do it today, I suppose. Let's plan on doing the baking soda lab. We've got so much time left. Actually, I'm going to put the baking soda lab off until this Friday. We'll cover it this Friday, and you'll have plenty of time to finish it before the end of the quarter. It's probably going to be our last lab of the quarter at this point. So I don't mind putting that off until this Friday. All right, Friday is when we're covering the baking soda lab. That'll be our last one. No, it's not due that day, Anna. Remember, that's a tentative schedule, right? So since we're not covering it until a week later than we said we're going to, we'll make it due a week later than we said we're going to. So it'll be due the Friday following. Okay? So we'll cover the baking soda lab this Friday. There is already a treatment of it on the web. So you can look at the run through that we did last year, and that's perfectly fine. Oh wait, is there a run through? I can't remember anymore. I think there is, but anyway, we'll do one together this Friday. Okay, if you want to look, I think there's already a video where I run through it, but if you want to wait until Friday, that's perfectly fine as well. I'll give you guys your own run through. You're worth it. All right, other than that, for Wednesday, please look ahead and review reduction oxidation reactions. It's not a hard topic, but there are a lot of rules for us figuring out what the oxidation number of an atom in a reaction is. So these reactions happen because one atom gets more positive in oxidation number and another gets more negative. Oxidation number is sort of a similar thing to charge, but there are things that don't have charges that still change oxidation numbers. Anyway, read the section ahead and we'll talk about it on Wednesday. All right. Cool. Well, it was fun to see you guys on Monday, and I'll see you in a couple of days. All right. All right. Peace.